So let's begin with our topic for today, which is chapter number 2, Kinematics, from GCE O-Level Physics 5054. I am Faraz Khan, and I'm here to teach you O-Level Physics. Now, the learning outcomes for this chapter would be speed, velocity, and acceleration. We're going to look at the different graphical analysis of motion, and then we're going to move on to free fall and terminal velocity. Now, speed, velocity, and acceleration. So, first of all, we need to understand the concept of distance and displacement. So, distance is the total length which is covered by a moving object irrespective of the direction of motion, which is only where only the magnitude of is of importance. Whereas when we're looking at displacement, it is the distance measured in a straight line. So it's a linear distance from point A to point B, which is in a specific direction. So both magnitude and direction are important when we're looking at displacement, but when we're looking at distance, only magnitude is of importance. So let's assume that a car is traveling at 5 kilometers. It travels 5 kilometers due east, and then it makes a U-turn and travels back a distance of 3 kilometers. So even though the car has traveled a distance of total 8 kilometers, its displacement would be only 2 kilometers. A pictorial representation of the difference between distance and displacement is right here, where you can see that the displacement is a linear direction from point A to point B, while the distance does not have a specific direction, and only the magnitude is of importance. Now, moving on to speed and velocity. Speed is defined as the rate of change of distance. So the speed is the distance moved per unit time. It basically tells us how fast or slow an object is moving. So the formula for speed is distance moved upon time taken, where speed is denoted by the letter V, distance moved is denoted by D, and time taken is denoted by T. A lot of times, bodies don't move in a uniform speed, so they do not have a constant speed. Like, let's suppose if you're traveling in a car, sometimes you're traveling fast and sometimes you're traveling slow. You don't have uniform speed from start to finish. In such cases, what we do is we take average speed. So for average speed, we take into account the total distance that is moved upon the total time taken of the whole journey. Whereas velocity is defined as a rate of change of displacement. It is speed in a specific direction. So when you're asked for the velocity of an object, you have to state the speed of the object and the direction of the travel itself. So for the formula of velocity, we would be taking displacement, which is a linear distance upon time taken, and in terms of average speed, the formula for average velocity would be the total displacement upon the total time. Now, some important speed that an individual must know from the exam point of view is the speed of sound, which is in air at room temperature is about 330 meters per second or 1200 kilometers per hour. And the fastest speed is that of light in a vacuum, which is 3 to 10 power 8 meter per second. Now, the SI unit for speed and velocity would both be meter per second. Now, moving on to acceleration. When we say that an object whose velocity, not speed, is changing, we can say that the object is accelerating. Now, if an object is moving at a constant speed but changes its direction as it moves, like for a stone that's attached to a string and you're whirling it around, or a car that is making a turn, you can assume that the object will either lose or gain its speed. So in such cases, we say that the body is accelerating. Accelerating is basically in the sense that it is defined as a rate of change of velocity. So the formula for which is the change in velocity upon time taken, and the change in velocity is the final velocity minus the initial velocity is the change in velocity. So acceleration is equals to change in velocity upon time taken, which is in symbols denoted as a equals to v minus u upon t. Now the SI unit for acceleration is meter per second square. Now a lot of times we see that when we say a car is making a turn and the body slows down. Now what happens is, in terms of acceleration, there is a negative sign attached to the acceleration figure, which means that the object is in retardation or it is decelerating. Now, moving on to the graphical analysis of motion. Here we're going to look at different displacement time graphs and velocity time graphs to understand what the body and different units are in reference to these graphs. Now we've got two different displacement time graphs, and what we need to understand is that the gradient of a displacement time graph gives you the velocity of a moving object. So now the y-axis on these graphs are displacement, and the x-axis on these graphs are time. Now we've done different plottings of a body moving at different times and with different displacements. Now for figure 1, you can see that the displacement s carries only a positive value, which means that the car has only been moving in one direction. And the displacement s also increases uniformly with time. And since it moves uniformly, we've achieved a straight line which shows that there is uniform velocity. Now if you have to find out the uniform velocity at each point, you can take average velocity, as it would remain the same within any interval. If you take any interval here, interval in the sense that, let's assume I need to take out an interval here for velocity. So what I need to do is I need to do change in displacement. Let's say I take a point here. Let's say we do it at 2, 1. The change here in y-axis is of the change in displacement, and the change in x-axis is a change in time. At any point, if you take this at any point, the change in y upon the change in x, which is the change in displacement upon change in time, would remain the same. With this triangle, it is 40 minus 20 upon 2 minus 1. So it's 20 upon 1. Velocity is 20. Here it's 80 minus 60 upon 4 minus 3. So it's 20 upon 1. Across the line, along the line, at any point, at any interval, your velocity remains the same, which is 20 meters per second. So your change in displacement per second is 20 meters, and it will remain the same along the line. Whereas it would not be the same in figure 2. Why? Because this displacement remains positive throughout the motion, but the displacement of the car is not moving uniformly. At points, you can see at points t equals to 1 and at t equals to 3, the car is standing still as the displacement is not changing at these points. You can see from 0 to 1, the displacement is 100. It's not changing. There is no change in displacement. At t equals to 3, for a very short amount of time, the car is standing still. There is no change in displacement. At points between 1 and 3, there is uniform change in the displacement. And at points between 3 and 6, there is also uniform deceleration. Now we need to understand that here we can see that these points, if you take a look at these, the gradient at these points is positive, which means that the graph and the body is accelerating. Whereas if you check at any of these points, you know that the graph is decelerating as the gradient is negative. So what we have learned from these graphs is that the average velocity is found by the change in displacement and upon the change in time, and a positive gradient of the displacement time graph indicates that the car is moving in the same direction as the displacement, whereas the negative gradient of the displacement time graph indicates that the car is moving in the opposite direction of the displacement. When the displacement is increasing, you can say that the body is moving in the same direction as the displacement, whereas in these points, when the displacement time graph is going down, you can say that the body is moving in the opposite direction of the displacement. Now, let's say I am trying to show you what the distance moved is from the time between t1 and t6. So let's say we have a body here. Let's say we have a body here. When it's moving away from its starting point, this portion is T1 to T3 because it's moving away from its starting point. It's going in the direction of the displacement. But when it turns at this point, this curve is where we can say the body is momentarily still as it's making its turn. This is where the displacement is turning. And now when it's moving towards its starting point, that is where the displacement time graph has a gradient of negative. Now, recalling our understanding from the displacement time graph, the average velocity is found by the change in displacement upon time interval. A positive gradient graph indicates that the car is moving in the direction of the displacement. A negative gradient means that the motion is against the direction of displacement. And a zero gradient means that the car is stationary. As we have seen, a zero gradient is on these curve points such as t equals to 3. Now, moving on to our velocity time graphs. Here, when an object is at rest and the object at uniform velocity, they both have zero acceleration since there is no change in velocity. Acceleration is the change in velocity upon the change in time. So when an object is at rest, there is no change in velocity, and when the object is moving at a uniform velocity, there is also no change. So the acceleration is 0. Now the gradient of a velocity time graph gives you the acceleration. So with steeper graphs, you can say that the gradient, with steeper gradients, you can say that there is greater acceleration. And the distance below these graphs is the total distance traveled. A negative gradient indicates that the object is retarding, or you can say it's decelerating. Now looking at some velocity time graphs, just like we said, so object at rest and object with uniform velocity, both have zero acceleration. It's a straight horizontal line. The gradient is 0. When there is constant acceleration, the change in velocity is uniform. It's a straight line. You can tell that there is constant acceleration as gradients at different points would remain the same. If I take a triangle and use it at different points along the graph, I can easily at any point the gradient remains the same, which means that there is constant acceleration. The same case with constant deceleration, the gradient, the slope remains the same at any given point, which means that the acceleration is constant throughout the journey. Whereas in non-uniform accelerations, you can tell that the gradients keep on changing. It's not the same moving along the journey, it's changing. the gradients keep on changing, which means that there is non-uniform acceleration. With non-uniform deceleration, you can tell that the velocity is decreasing, and the gradient also keeps on changing. So there is non-uniform deceleration. Now, if you look at this purple line, the velocity is increasing with time, whereas the acceleration is decelerating. As you can tell, because a steeper gradient means greater acceleration, here the graph is going from steep to gentle. So even though velocity is increasing, the acceleration is decreasing. With the pink graph, the velocity is increasing with time and the acceleration is also increasing as the gradient goes from gentle to steep. Now moving on to our next topic, which is acceleration of free fall. Now, the acceleration of free fall is what we call the acceleration due to gravity. When you leave an object in the air, there is a gravitational pull that accelerates the body towards the earth. Now, there are two cases where we will be looking at the motion of body with air resistance and without air resistance. So, looking at the acceleration of free fall without the air resistance, to observe the effect of a falling body without the air resistance, we carry an experiment in a vacuum container. So, there is uniform gravitational field without the air resistance. So, there is no air resistance that is being taken into account. There is no air resistance that is acting upon any body. So, what happens in this experiment is, when the object falls, the only force that is acting on the object is the gravity. So the object accelerates until it hits the ground, and this is called free fall acceleration. And since the earth pull on every object is the same, any object, regardless of its weight, let's say you take a feather, you take a coin, and you take a hammer, they both have different weight. But since there is no air resistance, as you're carrying this experiment in a vacuum tube, there is uniform gravitational field on every object, and all these objects would hit the ground at the same time with the same speed. All the objects will accelerate at 10 meters per second square, which is the gravitational pull. And the velocity time graph would be as such of a linear graph, such that of a x equals to y. Now, the direction of this accelerated motion is downwards, which is towards the center of the earth. And the acceleration does not depend on the masses or the weights of the falling bodies. So, any object, regardless of its weight, big or small, would increase their speed at the same rate. And if I were to draw a velocity time graph for this free fall without air resistance, it would be like this graph of constant acceleration, uniform acceleration, which would be 10 meters per second square. This graph would be the graph of free fall without the air resistance. Our second case is acceleration of free fall with the air resistance. So an object is falling near the Earth's surface and experiences a force called air resistance. Now, this is a very common phenomenon such that is applied in parachutes, it's applied in paragliding, hot air balloons. Now, all of these objects, as you know, the air resistance act upon these forces. It's the force that acts upon this falling body, and it's in the opposite direction of the gravitational pull. So it tries to slow the object down. And as the speed of the falling object increases, the air resistance also increases with it. And there comes a point when the object achieves terminal velocity. So the object is initially falling with a uniform free fall acceleration, which is 10 meters per second square. And then as the object starts to gain its speed, air resistance also increases with it. And when both of these forces are equal to the weight of the falling object, the object then starts to travel with a uniform velocity, which is called the terminal velocity, until it hits the ground. For the graph of the acceleration of free fall with air resistance, we're going to be looking at a few past paper questions, and there we will also discuss the graph of this acceleration of free fall with air resistance. So moving on to practice examples. The first question is that the graph shows how the speed of a car varies with time. Now the car is moving. Which statement about the acceleration of the car between 10 seconds and 20 seconds is correct? If you see in this graph, the speed is constant at 15 meters per second between T10 and T20. So, as we have learned about acceleration, it's the change of speed upon time, or the change of velocity upon time. Here, there is no change in speed. So, the acceleration is 0. Option D is correct. There is no decrease in acceleration, there is no increase in acceleration. The acceleration is not constant. The acceleration would be constant if the graph was moving in a uniform motion with a gradient. It needs to have some value attached to its gradient. It should not be 0. The gradient here is 0. It's a horizontal line parallel to the x-axis. So the acceleration is 0. Option D is the correct answer. Moving on to the next question. A student walks at a constant speed. He takes 100 seconds to walk 160 paces. The length of each pace is 0.80 meter. How far does the student walk in 50 seconds? So in 50 seconds, the student would be doing 80 paces, and if a length of one pace is 0.80, for 80 paces, it would be 80 into 0.80 meter, and the answer would be 64 meters by the unitary method of calculation. Moving on to the next. Now moving on, a cyclist takes a ride lasting 25 seconds. The diagram shows her distance traveled from the starting position, which varies with time. Now the graph is given, it's the distance traveled upon time taken, and they're asking what is the average speed for the whole ride. Now the formula for average speed, like we discussed, was total distance traveled upon total time. So the distance traveled by graph, as you can see, is 150 and the time is 25. So 150 divided by 25, the answer is 6 meters per second. Moving on to the next. A car begins to move, it speeds up until it reaches a constant speed. It continues to travel at this constant speed for the rest of the journey. What happens to the acceleration and what happens to the velocity of the car during the journey. Now it speeds up until it reaches a constant speed and it continues at the same constant speed. So the option A is both the acceleration and the velocity change. So when the car was speeding up, the acceleration was changing, the velocity was changing. So option A is correct. Only the acceleration changes. It's not true because, as we know, it was speeding up and then it reached a constant speed. So velocity was also changing. The acceleration was also speeding at the time when it was speeding up, and when it reached a constant speed, it decelerated to zero. So the acceleration was also changing, and option D is obviously incorrect. So the correct answer to this is A, both the acceleration and the velocity change. Moving on to the next. An object travels at a constant speed of 10 meters per second for 10 seconds. During the next 5 seconds, it accelerates uniformly to 20 meters per second. What is the total distance traveled by the object? Now, for this, we would be taking a look at the area below the graph, as the area below the speed time graph is the distance traveled. So we'll be breaking this graph into two parts. Here, the rectangle 10 by 10 would be part A, and then we were going to make a trapezium with sides 10 and 20. Applying the formula of area, which is 10 by 10, plus for the area of the trapezium, half by base, which would be 5, and the total of parallel sides, which would be 10 and 20, so 30. So 10 by 10 is 100 plus half into 5 by 30. The answer would be 175. As we'll be taking out the area under the graph by breaking it to two different parts, part A being the rectangle and part B being the trapezium. And the answer would be 175. Moving on to the next. At time t1, a stone is dropped from a stationary balloon. The stone reaches terminal velocity at time t2. Which rho gives the acceleration of the stone at time t1 and time t2? When the stone is dropped, the acceleration acting on that stone would be 10 meter per second square. Even though the velocity would not have increased as yet, the acceleration would still be the gravitational pull acting in its full force, which would be 10 meters per second square. But when the stone reaches terminal velocity, we know terminal velocity is a uniform velocity, and it carries down till the body hits the ground. So the acceleration at uniform velocity is always zero. So acceleration at t1 would be 10 meters per second square, and the acceleration at t2 would be 0 meters per second square, because terminal velocity is a uniform velocity and acceleration is zero at uniform velocity. Now the graph shows how the speed of a car traveling in a straight line changes with time. Which section shows the largest acceleration? As we have learned, the steeper the gradient, the greater the acceleration. We're going to look at the graph and see where the gradient is the highest. Where is the graph the steepest? And as we can see that at point A, the graph is the steepest. So here is where the acceleration would be the largest. So A is the correct answer. Moving on, the speed time graph represents a short journey. So the speed is uniformly increasing with time, and different distance time graphs are given. So which one is it? Now, if the speed was constant, and by constant I mean that if it was a horizontal line, the distance would look like the one in option C. But since the speed is increasing uniformly, the distance is going to increase in a non-uniform way such that it would be steeper as the time passes on, as the speed is increasing. So the correct answer for this is option A. As you can see that the gradient is getting steeper, it's increasing. And what's the gradient of a distance time graph? It's speed. And you can see that the gradient is increasing and this speed is also increasing here. So option A is the correct answer to this. A car travels along a road at 50 kilometers per hour. The driver applies the same braking force at the same place on a day when the surface is dry and then on a day when the road is wet. On the wet surface, how many of these distances are greater than on a dry surface? Now, the thinking distance would remain the same regardless of the situation. So a thinking distance would not change. The braking distance would change and there would be less friction on the road. And so the braking distance and the stopping distance would both increase on a wet surface due to low friction and the tire spin. So 2 is the correct answer for this question. Braking distance and stopping distance would be the distance is greater on the wet surface than on a dry surface. Moving on to our next question. The speed time graph for a falling skydiver is shown below. As he falls, the skydiver spreads out his arms and legs and then opens his parachute. Which part of the graph shows the skydiver falling with terminal velocity? Now, just like I said, we would be looking at a terminal velocity graph. This is what a terminal velocity graph looks like. As you can see in portion A, the speed is increasing and it's increasing till the air resistance starts to match it up. And as the air resistance is equal to the weight of the body that is acting downwards, the body immediately achieves terminal velocity, which is a uniform velocity, as you can see in portion D. This is the terminal velocity. It's a uniform velocity achieved after the air resistance has increased so much that it is equal to the weight of the body acting downwards by the gravitational pull. So option D is the correct answer for this question. Now, moving on to our next question. A steel ball is released just below the surface of a thick oil in a cylinder. During the first few meters of the travel, what is the acceleration of the ball? Now, it's a thick oil, so the resistance in the oil would be a lot. When you're dropping the ball, at the time when you drop the ball, you let the hand go, the acceleration is 10 meters per second squared. But since the resistance is a lot, the acceleration will decrease as it moves down. So in the initial first few seconds, in the first few centimeters of the travel, the acceleration of the ball would be decreasing. Moving on to our next question. A cyclist travels along a hilly road without using the pedals or brakes. Air resistance and friction are negligible. The speed time graph of a cyclist is shown at which point did he reach the bottom of the first hill? Now, when he reaches the bottom of the first hill, we're assuming that he's coming down, right? So, as he's coming down, his speed is increasing. He's using no brakes, he's using no pedals. So, the gravitational pull will bring the body down with a lot of speed. So when you look at the portion between A and B is the point the body is coming down. And at B is the point where where the body, the cyclist feels the shift of motion as it's the point B is where it reaches the bottom of the first hill and then it starts to climb up on the second where its speed decreases. So the curvature of the speed at point B is the point at which it is at the bottom of the first hill. So B is the correct answer for this question. Moving on to the next. A table tennis ball is released from the top of an evacuated tube. Which graph shows how the speed of the ball changes with time as it falls to the bottom of the tube? Since it's a vacuum, there is no air resistance. The speed is going to uniformly increase, and so A is the correct answer for this question. Moving on to the next, the speed time graph for a car is shown. What is the acceleration of the car at 30 seconds? Now at 30 seconds, we're going to check the change in speed upon the change in time. We're going to make a triangle. So 25 minus 5, the change in speed upon the time taken. So 25 minus 5 upon 30 meter per second square is the correct answer for it would have been the correct answer for this if they were asking for the first 30 seconds, but it is asking for the instantaneous acceleration of the car at 30 seconds. So as we know that when the gradient of the speed time graph is the acceleration, we're going to find out the gradient at 30. When the curve is turning, the gradient is a straight horizontal line as it turns. So 0 is the acceleration. A is the correct answer for 25. Moving on to the next, the diagram shows a parachutist in 4 positions after she jumps from a high balloon. At which position does she have terminal velocity? The terminal velocity is when the air resistance is maxed out, it is equal to the weight of the body falling, and so the acceleration is also 0 as the uniform velocity is achieved, also called the terminal velocity. So C is the answer because there is no acceleration on the body since it has achieved terminal velocity. Moving on to the next question, a skier is traveling downhill. The acceleration on a hard snow is 4 meters per second square, and on soft snow it's 2 meters per second square. Which graph shows the motion of the skier when moving from hard snow to soft snow? The gradient of the speed time graph is acceleration. So we're just going to look at the gradient of these graphs. So for the first 5 seconds, as you can see on the option C, 20 upon 5 is 4, and then between time 5 to time 10, 30 minus 20, 10 upon 5, it's 2. So C is the correct answer for this question. It would not have been B because this is deceleration. And if this was minus 2 meters per second square, then the answer would have been B. But this is plus 2, which means that the speed is increasing. So C is the correct answer for this. Moving on to the next. The graph illustrates the motion of an object. Which feature of the graph represents the distance traveled by the object whilst moving at a constant speed? Now looking at this, a constant speed is when the speed is a horizontal line. So area T is when the object is at constant speed. A very simple question this was. Moving on to the next, which quantity x is calculated using this equation? X equals to change in velocity upon change in time. Change in velocity upon change in time. A equals to v minus u upon t. A equals to change in velocity upon time. A is the acceleration. This was all for this chapter. Thank you so much. If you've got any questions, please comment them down on this video and I will reply to them. Thank you so much. Happy learning.